Okay. Good afternoon, everyone. Let's get started. Yeah, another reminder, please don't forget to take the quiz by tomorrow midnight. We don't want you guys to lose any points due to missing the grades or whatever. And also be careful, there's a time limit, and make sure you make your decision of those multiple single choice problems like within the time limit. Okay, so let us quickly review what we have discussed in the last lecture. So in the last lecture, we spent quite a while talking about the first distribution we discussed. The first one is called Bernoulli distribution, right? It represents a type of random variable which maps from a binary sample space, right? So every time we talk about the Bernoulli variable, you can associate with the flipping the coin as the example, right? You only have two possible outcomes. You see the heads up or you see the tail up, right? So the sample space will be just head or tail, right? And then the random variable underlying the Bernoulli distribution, we mentioned that the random variable is a mapping, right? Is a mapping from the sample space to a real number. So this mapping for Bernoulli random variable is just taken two possible values, 0 or 1, right? So basically we take we take the random variable at tail as 0 typically, and at head as 1, right? That's the definition of the Bernoulli random variable. And then we also require that the probability mass function for Bernoulli variable is as follows, right? So I'm just writing down here. So this is a notation of mass function. Basically, what is this represents the probability that your Bernoulli random variable value take A, right? And for the Bernoulli random variable, actually only have two values, either 0 or 1. Right? So A is either 0 or 1, right? So we require this PMF function to be A to the power of P and 1 minus A to the power of 1 minus P, right? So remember, this is a kind of unified form we mentioned in the class. It actually represents two cases. One is when A equals to 1, meaning that you say the head up, right? When you flip a coin, and this probability mass function is P, right? P here is not probability, it's just some number, which describes this distribution, right? Say P could be 0.5, could be 0.6. It depends on how you're gonna specify this particular distribution, right? When A is 0, so the value of F at 0 is 1 minus P, right? So that's the definition of Bernoulli distribution, right? Everyone's comfortable, right? Yeah, hopefully like everyone keeps this in your mind because it's very fundamental, although it might seem a little bit simple, right? And then we extend our Bernoulli distribution to the so-called binomial distribution. What is binomial? What kind of random experiments are typically or described by binomial distribution? Yes, exactly, right? So binomial distribution are talking about what are your experimental results if you just repeatedly run Bernoulli trials. Like imagine you're gonna randomly flip your coin for 10 times. Then I would like to say, what's the total number of heads you can see from these 10 trials, right? Of course, you can use other examples to illustrate this, but hopefully this is like a typical example will will be directly associated with binomial distribution whenever you start to look at this, right? So binomial distribution talks about, suppose you are doing a Bernoulli trial for multiple times, and each Bernoulli trial is independent with each other. It's like, okay, I toss the coin, I flip the coin for 10 times, but every time I flip a coin is totally independent with other trials, right? The result of my flipping this time has nothing to do with other trials. Then under this case, we would like to know, okay, how many times in total I could say the heads up, right? In a more general sense, we would like to say, okay, suppose you do a experiment multiple times, right? Independent multiple times. Each time your experiment give you either success or failure, right? Success means 1, failure means 0. And after you're doing this for 100 times, how many successes can you get in total? Maybe 50, maybe 60, whatever, right? So then what is the definition of the random variable underlying the binomial distribution? So here the x is defined as the total number of successes after all the trials, right? So suppose we are doing n experiments in total, n trials in total, and for each trial, we have the chance p to get success, right? Then we know that x can be as low as 0, right? The total number of successes, right? Maybe for all n trials, you don't have to see any success. All n trials are failures, right? But in the luckiest result will be, okay, all n trials are successful. In that case, n could be x could be n, right? At most n. So the value of the binomial random variable will just in the range from 0, 1, 2, 3 until n, right? One thing we should be very clear is the sample space, right? So we know that random variable x maps element in the sample space to this value, right? From 0 to n, right? So what consists of the sample space? Or every element, what does an element in the sample space look like? Anyone can give some hint? We just recall what we have discussed in Tuesday. It's not entirely accurate. So remember, in the original experiment, right? Just imagine we're playing a game. We flip the coin for multiple times, right? And what should we describe about the result? Once, yeah. Yes, the set. But here I want to be more accurate. This is not set. It's actual sequence, right? Yeah. So imagine you do it for 5 times, right? So that means that the result for the first time, the result for the second time, until the result for the 5th time will form one single outcome of your experiment, right? You should look at all the results after these 5 trials and form one single outcome, right? And your sample space should consist of all possible such outcomes, right? So that means your sample space it contains a lot of sequences of those results, right? So I just run the right could be H head, tail, head, tail, tail, right? This can be one outcome for your binomial experiment, right? You try, you run flip the coin for 5 times, right? And you see 5 results. They all together form one single result for your binomial experiment. Does it make sense? Any question? Okay, yeah. So like, of course, you have like many possible such results, right? Your first result might be tail, second might be head, head, tail, head, right? You name it. You just enumerate all possible sequences that represents when you try flipping the coin for 5 times, all possible results, right? So your random variable x actually are mapping from one sequence in your sample space to the total number of heads within this sequence. Right? Does it make sense? Right? See, if you look at this sequence, you know this sequence indicate one result. You're doing this 5 trials, right? The first flipping, you got head up, and then second tail, head, tail, tail, right? Then you run the variable x, evaluate on this sequence should be what? 2, right? Because x is defined as the total number of successes. Right? Here, success means that you see heads up, right? Question? N is 5 here. Yeah. Mm-hmm. No, it's not 5 sequences. N is like how many trials you conduct, right? The trials is not a number of sequences, right? So imagine like I flip the coin for 5 times. I can see 5 coin, I mean heads or tails, something like that, right? But this just for one possible outcome, right? So imagine after you flip the coin for the first time, you have 2 possible outcomes, right? Second time, you got another 2 possible outcomes, right? And if you do this until the last flipping, you still have 2 possible outcomes, right? And then your total number of sequences which indicate different results from all 5 trials will be 2 to the power of 5, right? Does it make sense? All right, let me make it more clear, right? So here, n in the binomial distribution just tells us how many independent trials you would like to do. And P, of course, is just the probability you succeed in each trial, right? But the result of this binomial experiments is not n, right? The total number of results. Why? Because every result is represented by a sequence, right? Each sequence consists of what you have saying after you do each trial. If you flip the coin, you see the sequence could be, as we just random written, is HT head tail, right? This is just one result. This result meaning that, okay, after I threw the coin for 5 times, what I'm saying about those heads or tails up, right? But there could be many other sequences represent the result as well. Does it make sense? Right? As to how many sequences in total do in the sample space, right? How can we calculate that? We just look at, okay, because this sequence will be just, contains 5 outcomes, right? Each outcome is either heads or tail. That means like in this sequence, every element has 2 possible choices, right? So you got a sequence of n elements. So you have 2 to the power of n, such different possible sequences, which form the whole sample space. Does it make sense? Okay, so this is very different from the Bernoulli distribution. Bernoulli distribution, you only have 2 elements in your sample space. Why? Because you only see heads or tail, right? One head or one tail can be your result, right? But when you do it multiple times, then the sequence of every outcome of doing your trials will form one result, right? So then there could be many combinations. Okay, so we spent quite a while in the last lecture to derive the probability mass function, right? We're not going to repeat doing this. Repeat the derivation again. Here we just want to refresh our mind of this form, the closed form of the probability mass function, right? So the PMF value at k, meaning that the probability of the binomial random variable x taking value k is this, right? So remember, how is this derived? Because this guy, x equals to k, defines the event, right? This event, remember, always remember, event is a set, right? This event consists of all sequences who contains k heads, right? And but for each sequence, the probability you see that sequence is p to the k, 1 minus p to n minus k. Why? Because the result for every trial is independent, right? So you see k has, then the probability you see all this k has p to the k, right? And for the remaining, you see tails, and the probability is 1 minus p to n minus k, right? And because you see every sequence has the same chance, right? And then the total probability of this event is just the probability of seeing a single sequence multiplying with the number of such sequences containing k heads. So this number is n choose k. Okay. I mean, if you are uncomfortable or feel blurred about this, I mean, I would suggest everyone to look at our slides and also try to derive this again, because this is really useful and important. Okay, so and in addition to the binomial distribution, another commonly used distribution is called geometric distribution, right? Geometric distribution are actually just to specify the probability for a particular type of sequence. That is, in this sequence, the first k minus 1 trials are failure, are all failure. Only the last trial, namely the case trial, is the success. And then the probability, so the random variable x, is defined as the value of the random variable x defines the first success at which trial you got first success, right? So x equals to 1, meaning that you get your first success after doing first trial, right? X equals 2 means that, okay, you get a first success in the second trial. And X equals to K means that, okay, you get the first success in the kth trial. That means like all previous trials are failures. Right? Then the PMF value for any K will be much easier because the probability of the event X equals to K only contains one sequence, right? The sequence is like have the first K minus 1 trials as failure, and the last one is success, right? We know the probability will always be 1 minus P to K minus 1 times P, right? Because the first K minus 1 trials are failures. Okay. So then we have the probability mass function for the geometric distribution as this form. Right? So the biggest difference from the binomial distribution is that the geometric distribution actually specify a single sequence to indicate the case where your random variable takes different values, right? It's not like binomial distribution. If I say two successes, then these two successes can appear in any two trials among my total n trials, right? And for geometric distribution, I only have one success, and this one success must appear at the last trial. Okay. Okay, so we want to reinforce our idea of these two distributions through this problem, right? Through this practice, the Monty Hall problem, right? We did a few in the last lecture. Let's just continue doing this, right? So in a Monty Hall game, we know that as the contester, if we decide to switch the door, we got 2/3 chance of winning. By switching door, it means like when you pick up gate 1, and then the host pick up gate 3 and showing a goat, right? And then you need to decide whether you're going to switch to gate 2 or you stay on gate 1. And let's assume we're just always choose to switching to gate 2, right? So in that case, we have analyzed that before. So we have like our decision will lead to 2/3 chance of winning the car, right? So now, suppose we play the game for 4 times, and we would like to know what's the probability of winning exactly once, right? So this is a typically binomial distribution, right? So your n will be 4, right? You do the experiment, you do the trials for 4 times, right? And you know, because our decision is always switching the gate, right? So your probability of success is always 2/3, right? So now, if we want to look at what's the probability of winning exactly once, that's just asking the probability of x equals to 1, right? Right. So this is just the PMF value at 1, right? So this one is computed. We can just use the formula we have discussed, right? So you're gonna do n choose k, right? So here n is 4, k is 1, and p to the power of k, right? K here is 1. 1 minus p to the power of n minus k, which is 4 minus 1 is 3, right? And p is 2/3, right? And how about you win 0 times? We just replace 1 by 0, right? So it's a 4, 0, p to the power of 0, 1 minus p to the power of 4 minus 0 is 4, right? So by the way, what is 4 choose 0. Just one, right? This is just some formula. You can check it out, right? But it's one, right? So for 2 and 3, right? For 2, 3, 4 times, we just apply the formula, right? So for winning 2 times, that means you're gonna choose 2 from 4, right? And p to the power of 2, 1 minus p to the power of 4 minus 2, which is also 2. Right? And if you want to look at what's the chance you win 3 times, right? From playing 4 games, now you choose 3 from 4, right? And p to the power of 3, 1 minus p to the power of 1, right? The last one, if you want to, if I look at what's the chance like you win all 4 times, right? That's a little bit greedy, right? But there's still some chance, right? So you choose 4 out of 4, and p to the power of 4, 1 minus p to the power of 0, right? So what is 4 choose 4? It's still 1, right? Okay. Now let us look at the second question. What's the probability of losing the first 3 times and winning at the 4th try? In other words, what's the probability of you keep losing until you win at the last try? How do we calculate that probability? Is it still binomial distribution? So it's a p to the power of, so probably I should follow what you said exactly. So it's 1 minus p to the power of 3, right? And p to the power 1, right? Do we need to put a factor like 4 over 1? Why? Yeah, exactly, right? So remember, in this case, the random variable we're talking about is not binomial random variable, it's geometric random variable. Why? Because we're specified you only win at the last trial, right? You cannot, I'm not asking the chance that you win at first trial, second trial, third trial. We're asking, okay, you keep losing until you win at last trial. In that case, the random variable, it follows geometry distribution, and this is the probability mass function, right? So when you calculate the PMF, it will be something like this, right? And there's no a constant factor like n choose k. Okay, any questions so far? Great. Hopefully this in class practice will be very helpful for you to understand those definitions and also, our homework problems. Right? So so far we talk about this Bernoulli experiment and repeated Bernoulli experiments, namely binomial distribution and also the geometric distribution, right? So there are some like key notations worth your attention, right? So first we need to specify the number of trials, right, which are usually denoted as n. And second, we usually use k to represent the number of success. Right? In a binomial, it just means the total number of successes, right? And then in a geometry, it means like at which trial you gain your first success, right? And the last thing, which is also very important, is p, which parameterize the probability of success for each single trial. It's like, okay, when you flip a coin, what's the chance you see the head, right? Okay, any question? Great. So this is about the discrete random variables we have introduced. And of course, for discrete random variable, there's a a very big family. We'll just start with those very fundamental and very widely used ones. But there are a lot of other discrete and random variables. If you're interested in, you can take a look at the book, and also we haven't talked about like categorical distribution. So this is actually very important for multi-class classification. Sorry, I'm from the machine learning domain. I'm more like leaning toward giving examples from machine learning applications, like in the image recognition. You want to say whether it's a cat, whether it's a box, whether it's a dog, deer, and all kinds of stuff, right? You can imagine the objects appearing in the image could be 1,000 different categories, right? And then you the one thing you want to look at, okay, is to classify the image into a large number of categories. And then there naturally there will be some need, like can we construct a distribution to describe the probability your image belongs to categorical 1, 2, 3, 4, 5, 6 until 1,000 or even 10,000. So for that type of applications, you need some categorical distribution, right? And the Bernoulli distribution, you can view like, okay, I only have 2 categories, right? Success or failure. It's dog or not, or it's not dog. It's cat or not, it's cat, right? But if you extend the number of the categories to be many, and then Bernoulli distribution will not be sufficient, right? We need to describe other a more general discrete random variables and their distributions. Okay, so our next topic is to introduce another type of random variables, which is called continuous random variables, right? So you see, it's kind of like complementing each other, right? The random variables, we talk about discrete random variables, and then we're now talk about continuous random variables. So actually, continuous random variables are very, very rich. You see like most commonly used distributions are based upon the so-called continuous random variables, and even those, for example, the fundamental theory is called central limit theory or law of large numbers. They are all based upon the continuous random variables, right? Okay. So let us first record the definition of random variables. So we repeatedly emphasize, I mean, again, right? The random variable is a function, right? It's a function that maps from some sample space to a real space, right? So the sample space comes from like the original random experiment or random things you're interested in, right? And when you observe that, you might have like different outcomes, right? You have a lot of different outcomes. That's why it is random, right? We cannot make sure like every time you will see the same outcome. So the random variable maps the elements in a sample space to a number in a real space. And the sample space we have discussed so far are all discrete sets. If we could remember, right? For the Bernoulli random variable, the sample space is just say heads and tail, right? Or 0, 1, whatever, you name it, right? And for the binomial random variables or binomial distribution, the sample space are just the sequence of binary outcomes, right? Each outcome comes from one child, right? So like if you flip the coin for 5 times, right, your sample space will consist of all sequences of 5 outcomes for flipping the coin, right? Like S, tail, 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 S, tail, S, tail, tail. Name it, right? Just enumerate. Does it make sense? Right? So you see that, okay, all those sample spaces are discrete. and finite. Right? But in real world, I mean, because the random experiments and the random phenomenon are everywhere in this world, right? So in the real world, is there a case such that the sample space is continuous? Is it possible? If it's possible, can you name it, right? Can you give me some example? You mean the length of bridge? Yes. Yeah. Yeah. Actually, any quantity, uh, you know, it comes out it comes from some like a random process, which you don't know the mechanism, right? If that quantity is continuous, the sample space must be continuous, right? Uh, in addition to the bridge length or curvature, we can think about that like temperature, right? The raise of your uh, the temperature gauge, right, is definitely continuous, right? Um, and this temperature is obviously random, right? You don't know, or you don't know. I mean, the exactly precise procedure that uh, generates the final temperature, right? From any physics, you know, okay, the temperature is just some kind of macro summary of the uh, activities of molecules, uh, right? There's so many molecules. They're bumping with each other, right? So that's too many. No one is gonna tell uh, overall how much temperature it is, right? You can just measure them from some like uh, uh, from some device, right? And then they you get the read, right? And this read is continuous. Another example could be, say, the stock price. And although the stock price won't be some irrational number, but it's continuous number, right? And because of the underlying mechanism, no one can really predict the exact number of stock price, right? The stock price is continuous. Okay. So if the sample space omega is continuous, then we can use more advanced tools to analyze the random variable. Remember, random variable is a function, right? It maps from some domain omega. Omega here is the sample space to some a real space, right? If omega itself is continuous, then this x becomes a function from a continuous domain to another continuous domain, right? And then x can take on a continuum of values. That kind of like connects to a calculus 1 and calculus 2, right? We have taken during our undergrad school. Then we would like to know, okay, because x maps any number in a sample space to a number in a real space, right? Then we can take a look at what if an infinitesimal change in the sample space will cause what kind of change in the value of the random variable, right? That's kind of like real analysis. Does it make sense? To be more concrete, right? To be more concrete, let us use an example, right? And here we're not talking about temperature, stock price. We use another example to illustrate how we can generalize our random variable from discrete to like continuous. So this is random phenomenon we're interested in. We record the time elapsed from the start of the class until the last person arrives, right? Um, so our course, take 80 minutes, right? So this time t, the t is the your observation, right? The observation of the time elapsed from the start of class until last person arrives, right? So obviously, your observation can be 0, smallest, right? Or at most 80 minutes, right? Because our class lasts at most 80 minutes, right? So the range of this time record is between 0 and 80 minutes. Does it make sense? Right? So now if we want to look at the probability of t equals to 5, right? So t here, we haven't talked about, it's not a random variable. It's just what you observe. It's like you see the heads or you see the tail, or you look at the temperature read, right? And you want to look at what's the probability that you say the last person comes to the class 5 minutes after the starting of the class, right? So we want to look at what's the probability of t equals to 5. Right? Okay, so now when we record the time, we could take different granularity, right? I can count by, say, by minutes. If I count by minutes, then what's the sample space? What? Yes, right? So let us consider we kind of like vary the granularity we record the time, right? So if we first, for example, suppose I use a very rough and very the recording way, right? I just count by minutes. Then my sample space will be just 0, 1, 2 until 80, right? Meaning that, okay, 0 minutes elapsed after the first last person arrives at class, or 1 minute, 2 minutes, 3 minutes until 80 minutes, right? So so we know that, okay, this observation, right? This observation of your the time, right, will belong to this sample space. And now let us do not make any fancy assumption, like complex assumption of this probability. We just assume, okay, it is kind of like a have the equal chance. The last person arrive at the class has the equal chance. So it might they might get here like 0 minutes after class, or 1 minute after class, 2 minutes, have the same chance, right? So now in this sample space, what is the probability of t equals to 5? Yes, 1 over 80, right? So here t equals to 5 represents this event 5, right? The size of this event is 1, and your size of sample space is just 80, right? Does it make sense? Right? Any questions so far? Okay. So now suppose I have a better watch, right? I have a better watch, and this watch can count per half minutes. I mean, so I can count 0 minutes, 0.5, 0.5 minutes, 1 minute, 1.5 minutes, and 2 minutes, and so on. So I have more precise counting of the time, right? So then in this case, right, what is our sample space? Yes, exactly. It's double the sample space we just mentioned, right? So because I have a more possible outcasts in my sample space, so it is 0, 0.5, maybe I write it as okay, 0.5, 1, 1.5, 2, 2.5, and 5, 5.5, until 80, right? So in this case, right, with my better watch, right, if I still want to calculate the probability of t equals to 5, what's that probability? Yeah, 1 over 160, right? Because now your sample space increases by double, right? Okay, so we can keep um, increasing the granularity, meaning that I'm gonna use a more and more precise watch. I say, suppose my watch can record every second. Right? Then my sample space will be, you can imagine, will be much larger, right? So I want to ask, what's the size of a sample space? I'm not going to enumerate every second throughout this 80 minutes. That's too many, right? But I just want to ask you guys how many elements you will be in the sample space if I can count every second with my watch. Yes, right? Just because every minute is can be partitioned into 60 seconds, right? You just enumerate every you just replace every zero now by 0 second, first second, second until 59 second, and 1 minute, minute one, meaning that okay, 60 second, right? So in total, your size of sample space will becomes 80 times 60 is 4,800, right? Then in this case, what's the probability of t equals to 5? 5 minutes means that 300 seconds, right? Then what's the probability? Yeah, 1 over 4,800, right? So that things becomes like more and more crazy, right? So now you can imagine I have like some even more and more precise a watch. Like I can use Atom clock, right? I can use whatever clock, and eventually you can count the time so precisely you can count continuous seconds. If you count continuous time, right? What's the size of sample space? Yes, it's infinite, right? Because even in the range between, so in this case, I mean, maybe we're going to use another commonly used notation. It becomes a continuous interval, right? Between 0 and 80, and this omega, this whole space, this whole sample space contains every possible second in this continuous region between 0 and 80, right? And then the sample space is infinite, right? It's infinite size because there are numerous numbers within its range. Then under this case, what's the probability of t equals 5? Yes, intuition is correct. Although t equals to 5 must mean some time point inside this region, right? But there are so many elements in that. It's infinite number of elements in that. That means you're gonna divide 1 by infinite. So it is 0. So you can see that as you grow your sample space to be larger and larger, and eventually your sample space becomes infinite, then your probability for you see a single outcome becomes 0. Right? You see a single outcome means that okay, you see it exactly the time is 5. This probability becomes 0. Does it make sense? Okay, let's take a rest for 5 minutes and then we continue talking about how do we deal with this case, right?
zero inclusive, what if the probability is 1/81 instead of 1/80?
Oh, okay. Yeah, that's a good point. Yeah. You can put down here. This is just an illustrative example to show that uh you can actually put all the denominator as 81 by well
Yeah, we're
oh,
just
yeah.
trying to show that
Yeah.
it pushes zero, right?
Yeah, it pushes zero. Yeah.
But usually we include zero in some space.
Yeah, we include that. Okay, that's good catch. Yeah. Okay, so let's continue. Yeah, I think during the break, someone pointed out there was a counting issue for our analysis. Actually, if we count by minutes, like 0, 1, 2 to 80, your sample space should contains 81 elements rather than 80. Yeah, thanks for the catch. Yeah, you're absolutely right. We should replace this guy by 81, right? And of course, take it half. This might be not 81, it's 81 plus 80, something like that, right? But anyway, the point here is to show you that when you gradually increase the sample space originally was discrete and finite, right? When you gradually increase it to more and more until at the limit, your sample space becomes continuous. Then you see that the probability you see a single outcome will approach 0, right? So t equals to 5 represent an event. This event contains a single outcome, right? And this outcome is 5 minutes, right? And a sample space, when it only contains minutes, right? 0, 1, 2, 80, well, you got probability 1 over 81, right? Or it's not 80, right? If we contain like minutes on half minutes, and it becomes like a 1 over 160 or 1 over 81 plus 80, maybe 1 over 161, right? So, but when you keep increasing, right? It's about like I take a more and more accurate watch, and until eventually my watch is so good such that for any possible time, I can record it, right? That means your sample space becomes a continuous interval. It's between 0 and 80. Then you can imagine your sample space contains infinitely many and uncountable possible time values, right? And then if you calculate the probability, you only see a single outcome. This probability approaches 0. So this is one very significant difference from discrete random variables. But discrete random variable, okay, that's no problem. You can calculate, you can quantify the probability. You only see one single outcome, right? But in continuous case, this is always 0, right? So, but if we instead look at another type of event, that is your time is inside another range. Say it's in the range between 5 and 6. So remember, this inequality represents an event, right? This event is actually another set, which is a range, is the interval 5 and 6. So now I want to ask, what's the probability you see this time within this range? Any guess? Yeah, your intuition is absolutely right, right? So it's just the size of the range over the size of the sample space. But here size, it doesn't mean like how many numbers, how many elements in size. Instead, it just means the size, right? The length of the range. And the length of the range for 5, 6 is 1, right? The length of the sample space is 80, right? So it's still the probability 1 over 80. So you see the difference here, right? So for the continuous random variable, we can only get non-zero probability for events that is inside the range. This range is also infinite and uncountable, right? And then we can calculate the probability by looking at some kind of measurement of the volume of the length of the event over the volume or the length of the whole sample space. Right? For the real space, one-dimensional case, this range is really just measured by length, right? Length is a right endpoint subtracted by the left endpoint, right? So we can still calculate that, right? But in a more general case, yeah, this will be out scope, will be out of scope of this class, but just for your reference, we have to define some measure over those sets. Measure means that I'm gonna give you a way to quantify the volume of the sets. But the volume of sets doesn't mean how many elements in the sets. It just means volume. It's like, look at this table, right? How large is this table? You tell me, okay, this might be 1 square feet or 2 square feet, right? But if you look at how many atoms are laying on this table, infinite, right? So it's the same thing, right? So I can still quantify the size, the volume of this table, right? Even this table might contain like infinite many atoms, right? It's the same thing here, right? So in general, you have to define your measure over the whole sample space and your measure over every possible event. This event is meaning a subset, right? See, this 5, 6, and then you divide these two measures. Right? So that's why the real probability theory must be defined on measure theory. I only give you the rigorous definition of measure function, and you have to talk about the measurable functions. You can define what does really mean. What's the probability measure? But this is we won't talk that in depth because you have to introduce too many additional concepts on that. But here we want to just give you the most important intuition here. So that is like your sample space. When the possible number of outcomes are so many such that it becomes continuous. By continuous means like, okay, your elements in the sample space will be uncountable, will be infinite. And then how do we calculate the probability? Okay, any questions so far? Okay, so, and then if we have some continuous random variable, what kind of mathematical concepts or definition do we care to characterize those random variables? Similarly, similar to the discrete random variables, we also consider two functions. One is called the probability density function. This is counterpart to the probability mass function. But essentially, they're different. They have different meanings, right? We'll talk about it later, right? And the second one is called a cumulative distribution function, which is essentially the same as the CDF function defined for discrete case. Okay, so first, what is a probability density function? So the probability density function is defined in this a little bit indirectly. So if there is a positive function, f of x, but actually it should be non-negative function, such that it is non-negative for every possible value of the random variable x, and also the integration of this function f from minus infinity to infinity is 1. If we have such a function f, right, which is non-negative, and integration from the whole domain, right, is 1, and the probability of the event defined by A less than equal to value of X less than equals to B, right? The probability of X between A and B can be calculated by the integration of this function in the range A and B. Then we call F is the probability density function. So it's a little bit, to give this definition is a little bit tedious, and it's not very, it's not very like intuitive. It's not like when we talk about PMF, right? When we talk about probability mass function, we just say, okay, that is essentially the probability of the event defined as X equals to some particular value A, right? This is called probability mass function, right? But here we use a kind of a very like detoured way to define that, meaning that okay, if we have some non-negative function, the integration over the whole domain is one. Also, any the probability of the random variable X falls in any range can be represented as an integration of this function in this range. Then we call F as a probability density function. The reason to introduce is because we want to ensure it's rigorous, right? Because the probability density function is not the probability of X equals to A, right? Maybe I should write it in this way, right? The probability density function at any point, like n A, right, is not the probability of the event defined as the random variable value takes A. Why? Yeah, to be more explicit, right? This guy from our discussion a moment ago, this guy actually is zero, right? For continuous round is zero, right? And this guy is not always zero, right? Actually, in most cases, it won't be zero. So that's why this is a key difference between the PDF and the PMF. PMF has probability meanings, meaning that okay, it means the probability for a special type of event, meaning that okay, I say some particular results which gives the random variable to be A, right? But for probability density function, it doesn't have like explicit probability meanings. It doesn't mean the probability of seeing any event. Does it make sense? It's more like, okay, when I say the probability of some event, say less than B, is kind of vary, right? This is the probability of an event, right? It's vary along with B. And this variation, it is continuous. Then if we can take a differentiation, that is the PDF. It's just like you see a continuous function, right? And the continuous function, the function value changes continuously along with the change of the input. And then you can consider if you can take the derivative and say the change rate, right? That's what calculus 1 talks about, right? Derivative and integration. And the PDF is defined in this way. It actually reflects how the probability of some type of events varies. The rate of such variation. That's the PDF. It's not, it doesn't represent the probability of any special type of event. So if you feel like uncomfortable of what I'm saying, is fine, because we're going to come to that point later, especially when we talk about the CDF. But this is definition. Is any question regarding the definition of the probability density function? Okay. Yes. 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 So PMF, when we talk about PMF, it just talk about discrete random variables. Your sample space is discrete, and we're interested in looking into the probability that your random variable takes some particular value. In that case, the probability is non-zero in most cases. I mean, and then we define the PMF is just your random variable takes some particular value, right? But for continuous case, as we mentioned, like if we take analogy to the discrete case, the probability of X takes any particular value, right, will amount to 0, right? Because your sample space is so large, contains so many elements, right? But the PDF is not defined in this way. The PDF defines a good thing, a good representation of the whole probability such that for looking into any events in the range, right? Any events represented by range, it can be calculated through the integration of the PDF function in this range. That's the definition of the PDF. Any question? Okay, so if we further introduce the cumulative distribution function, I will kind of like deepen our understanding of the PDF function, right? So what is the CDF? CDF, the definition of CDF is exactly the same. The definition of CDF for continuous random variable is exactly the same as for continuous random variable. It just defines a type of it just defined as the probability for a type of events. This type of events is defined as X less than or equals to A. Right? Remember, this is actually a particular type of events, right? It contains all the elements in a sample space, although now the sample space should be continuous, right? Such that when X is evaluated at this omega, it is less than A, right? Less than or equal to A, right? So it's still, the CDF function is still defined as the probability for this event. But of course, this event is indexed by A, right? Right? Different A will correspond to different set, and it will give you different probability, right? But for the continuous case, because the sample space omega becomes infinite and continuous, right? So you can imagine the change of A, when you change the A continuously, this range, this set actually is a range, right? Is also changing continuously. So that means, roughly speaking, in most cases, this guy is differentiable. And it's differentiable, and it can be represented as the integration of the PDF function fx from minus infinity to A. So in other words, you can view PDF comes from the differentiation of the CDF function. Okay, let's just stop here today. Next week, we're going to continue our discussion about CDF PDF function for continuous random variables.
Or can you like explain of the and choose K mean?